Hello and welcome. In this video, I'll be covering the solutions for the Unit 5 test review. So let's go ahead and get it started. The first one just wants us to find the inverse of a relation. So remember the inverse, we just swap x's and y's. So this will essentially just be the set of ordered pairs such that I swap each x and y. So 1, 8 will turn into 8, 1. The next one, 4, 0 would become 0, 4. One after that, -5, -1 is now -1, -5. And the very last one, I've got -6, 2 turn into 2, -6. Move on to the next couple. Just says to determine whether the function is one-to-one. So what we can utilize is a horizontal line test. So if I did that really quickly here with number 2, a horizontal line would intersect that horizontal line infinitely many times, so this one would not be one-to-one. Whereas the linear function for number 3 would pass the horizontal line test, so that one would be a yes. If we move on to the next grouping, it wants us for all of these to first determine whether it's one-to-one. So what we can do for this one, since we don't have a picture, is just think in terms of would I ever get the same y by plugging in an x, or is this an increasing function the entire time? So the harder one to probably do will be maybe to think in terms of number 5, but let's just assume that it will be one-to-one and try and solve it when it gets to that. So anyway, number 4, it's a linear function. It's coming down the page because of the negative slope the entire time. So since it's always doing the same thing, remember one-to-one was either always increasing or always decreasing. I think I just said it was only increasing, but it could always be decreasing as well and still maintain being one-to-one. So this one is one where I could swap the x's and y's. So this will now become x equals -2y plus 1. And then go through and solve for y. So first thing would be subtract the 1 over, so I'd have x minus 1 equals -2 times y, and then divide by -2, and that result now would be our final result. Since this is one-to-one, I'm going to go ahead and use the inverse function notation and just call this a x minus 1 over a -2. If you wanted to distribute the negative from the bottom through on top, you could also have this written as 1 minus x over +2. But it's kind of up to you. I feel like just leaving the negative on the bottom is good enough. Looking at number 5, I'm just going to go ahead and swap the x's and y's, and we'll assume that this is one-to-one. I'll just keep an eye out for potentially any plus or minus symbols that would make it such that I get 2 answers for one thing that I plug in. So we'll find out what happens here in the end. This one immediately has a fraction, so I would go ahead and multiply both sides by the denominator of that fraction. That way I clear the fraction. So now if I were to rewrite this in this white space up here, I could distribute the x through and get 4x minus x times y. And that would just equal, because the denominator on the right has canceled, just a plain y. So it seems like since I'm trying to solve for y, I should at least get the y's near each other. So I'm going to add that xy term over. So I've got 4x equals y plus x plus y, or x times y, sorry. Now notice both of those have a y, so I can actually factor in, or factor one of those y's out, which would leave me y parenthesis. If I take y out of itself, it needs to leave a 1, and then plus, if I took the y off the second term, it would leave a plus x. That then allows me, because there's only a single y, to solve for it by just dividing by what was in the parenthesis, which was a 1 plus x. So those cancel, got y by itself. I don't see any plus or minus symbols, so this seems like it would be a one-to-one function. And so I'll go ahead and say that the inverse function of this is, in fact, 4x over a 1 plus x, or if you wanted to write it as x plus 1 because you like the x first, that would be fine. For number 6, this one, it just wants us to determine whether it's one-to-one. Well, this would be a parabola. That definitely fails a horizontal line test, right? If I draw a parabola, I could draw a horizontal line through it. It touches more than once. So this is one where the inverse does not exist unless I were to do some form of domain restriction, which the problem is not telling me to do. All right, number 7 now wants us to show using compositions of functions that the two functions presented truly are inverses. So that tells me that my two compositions are going to be f of f inverse and f inverse of f. So I'll make sure, I'll write that here in a second, just to make sure I have enough room. So that basically, this first one means that the second function is going to be plugged in everywhere I see x in the first function. So this would become a 1/2 parenthesis, where the x is, I'll put the other function 2 times x plus 3, and then minus 3. And so if I look at what we can do, if I multiply the two parentheses there, it looks like the 1/2 would cancel with the 2. So I can now say that this really is equivalent to x plus 3 minus 3, which a plus 3 minus 3 also cancels, so this turns into x, which is what I wanted it to turn into. So notice, yes, I got working one way, it turned right back into x. Now I need to do the other possible composition, which is f inverse of f, so basically just switching the order up. So that means now the function on the left is going to go in place of the x that I see on the right. So this will start with a 2 parenthesis, then I've got 1/2 x minus 3, and then plus a 3 inside my parenthesis. Well, I can immediately see that a minus 3 plus 3 cancel each other out, so this would be able to be rewritten as 2 times, and all that's left is 1/2 x. Well, 2 times 1/2 also should cancel each other out, turning into 1s. So this would also leave x. So since both of those turned into x, then at that point we can say with confidence that yes, that truly was the inverse of f. For number 8, this one's telling me it's already a 1-to-1 function, so I don't have to do that analysis. It just wants us to first find the inverse. So the first thing I would do is swap the x's and y's, so it would be x equals y cubed plus 4. So immediately I'm going to start trying to get the y by itself, so I would subtract the 4 first. That gives me x minus 4 is equal to now y cubed. And then now to cancel a power of 3, I would take a root with an index 3, otherwise known as a cube root. So I can now say for this one that the inverse function for the f is equal to the cube root of this x minus 4. Then it says to go ahead and graph each on the same set of axes. So if we think in terms of what the original points are for maybe x cubed, we could deal with that. So x and x cubed originally would be like -2, -1, 0, 1, and 2 as numbers that we could plug in. And their corresponding pairs, when I plug it into just plain x cubed, are -8, a -1, a 0, a +1, and a +8. So when it comes to making like my actual f t-chart, it's going to be x and now f of x. And I need to think in terms of what's this plus 4 doing? Well, the plus 4 should be moving it up 4, which basically means add 4 to y. So that would be kind of the interpretation that I have if I needed to shift something up 4 places. So that means all of the x's are going to stay put, but all of my y's need to increase by 4. So -8, if I add 4 to that, would be -4. -1 if I add 4 to it would be +3. 0 if I add 4 to it is 4 itself. 1 if I add 4 to it is 5. And 8 if I add 4 to it would be 12. So that last point looks like it's actually going to be a little bit too big for the grid, so I won't have to worry about that one. When it comes to the inverse, I'm just going to take that same t-chart, but actually plug the y values in for x's and then the x values in for y. So basically I just swap those two columns and plot those points. So first I'll start with just graphing the f function, just plotting these points. So I've got -2, -4, I've got -1, 3, 0, 4, 1, 5, and then 2, 12 was a little too big for the grid, so it would look like a function that kind of snakes through these 3 points and then gets a little steeper again as I go. The inverse, I would just take each of those ordered pairs and swap the x's and y's. So instead of plotting -2, comma -4, I'm going to go to -4, comma -2, and then go to +3, -1, then go to, or that was +1, sorry, +3, -1. There it is. Next one is going to be at 4, comma 0. One after that, 5, comma 1. So once again, I'm just taking the y's and x's and just swapping them if you weren't able to follow along with what I had. And the last one would be 2, 12, which would be somewhere off the grid over there. And so now I'll just do my best to try and sketch and connect those points with a nice smooth curve. And it really should look like a mirror image across that diagonal line of y equals x. If I just go ahead and maybe sketch that on there, the fact that they met along that line when I graph those seems reasonable, and they do in fact look like mirror images of each other. The only thing it looks like I left off with was a random arrow on the far left, or on the far left bottom. But now we've got our two functions being graphed. So notice the one in red was the f function, and the one in blue was the inverse of f function. Moving on now to number 9. This one wants us to just graph. It looks like there's only really one transformation. So if I just think in terms of what do I see and what do I know, I see addition inside the function. So addition inside should move it left, whatever that amount is, which in this case is just left 1. So let's come up with our original points for the e to the x function. I'll try that x again. And then we'll end up coming up with a different t-chart for the actual f of x function. So I'll make it a little bit different color. So this will be the one that I actually plot the points for. Now, this also does have a horizontal asymptote that I can keep track of, that potentially could change depending on what is happening. But in this case, if I take a horizontal line and go only left 1, I feel like it's going to stay the same at y equals 0. So I'm going to go ahead and just commit, because the left 1 is not going to change a horizontal line, that the horizontal asymptote still would be at 0. Now as far as our t-chart is concerned, plugging in -1, 0, and +1, and maybe +2 might fit. These are ones that we've done a fair amount of times in our homework, but we could just type this into the calculator as well. So e to the -1 would be like 1 over e, and 1 divided by e, if we type that in, gives me approximately 0.4. E to a power of 0, anything to a power of 0 is 1, so that one's just a 1. E to a power of 1, well, e was approximately 2.718. Going out to the tenths should be good enough. And then the last one would be e squared, which comes out as 7.4. So looking at our grid only going up to 6, I probably won't have to worry about that one. Now what's happening is I'm going left 1, so that should mean I'm going to take away 1 from the x's, because if I go left they should decrease. So if I just take the 3 x's that I have and decrease them by 1, that would give me a -2, a -1, and a 0. But the y values of 0.4, 1, and 2.7 would not change. So now let's go ahead and put these in action on our grid. I have a horizontal asymptote at y equals 0, so I know I'm not going to cross over the x-axis. I've got my first point at -2, comma 0.4, which would just be barely above 0, -1, comma 1, and then 0, comma 2.7, and then the last one, if I wanted to go to it, would have been at 1 and 7.4, so it would have been a little bit higher up on the grid. So if you wanted to have that just as an approximation so you know how steep to make it, go for it. But now we just connect the points in a nice smooth way and finish our graph with a couple of arrows, keeping in mind that we're technically flattening on the left. We're not actually going to cross over 0, so just make sure that it seems as though it's getting super close to it but not actually going below it. Number 10 here is now a relatively similar example in the fact that I'll probably want to create a t-chart, but this time it's more the log function. So it's better to, for this one, select my y values and see what power on the 3, if I put that on the 3, I would end up getting. So this really, for the first one, would be like 3 to a -1 power. What is that x? Well, 3 to the negative 1 is not negative, but 1/3, which is approximately 0.3. 3 to a power of 0 would equal 1. 3 to a power of 1 would equal 3. And then 3 to a power of 2 would equal 9. So it looks like that last one, once again, is going to be potentially a little bit too big for our grid, but we do still have a couple of shifts to worry about. So notice this one had 2 different shifts. I've got the x minus 1 on the inside, and then I've got the minus 2 on the outside. So the minus 1 that's inside, that's really going to move it to the right one. The minus 2 on the outside is going to move it down 2. So as far as what should change on my t-chart, I'm just going to go ahead and set it up for this specific function. If I go to the right one, I should add 1 to x. If I go down 2, I should take away 2 from y. So if I just break this down into those 2 steps, I'm going to increase each x value by 1. So 0.3 would turn into 1.3. 1 would turn into 2. 3 would turn into 4, and 9 would turn into 10. So it looks again like that last one still is going to be too far off grid, even after this shift. And then down 2 it means decrease each y by 2. So negative 1 take away 2 would be negative 3. 0 take away 2 is just going to be a negative 2. A 1 take away 2 is negative 1. And 2 take away 2, not that it's going to fit, is 0. Now keep in mind these also for logarithms have a vertical asymptote of x equals 0. Since I did have a horizontal shift, this should have a new vertical asymptote at whatever would be 1 to the right of 0, which should be positive 1. So I'm going to start by just putting positive 1 as a vertical asymptote on our grid over here, so I make sure I don't cross over it. And now just plot some points. So I've got 1.3, which is just a little bit to the right of that vertical asymptote, down at negative 3. I've got at 2, I'm down at negative 2. And then I've got at 4, I'm down at negative 1. And then the last one was all the way over at 10. So it seems to me like I probably shouldn't cross the x-axis on this grid because 10 would be even further off. So I'm just going to kind of flatten and get it at least going in that general direction where it would cross at 10, 0. But that would be my logarithm graph for this one, at least the one that was a log base 3. So again, kind of what to take away to create our t-charts. You could also do this with key points. The key points for this are 1 over the base, comma negative 1, 1 with 0, your base with positive 1, and your base squared with positive 2. So you could also have done it with just like remembering key points for this graph instead of doing a t-chart, but then actually physically counting or moving the points right one place and then down 2 places from their locations, plot those points, and then we would get the same points that we just plotted here using the t-chart system. As far as the number 11 is concerned, this really is just a calculator exercise. So if we were to type these in, the natural log of 6.1 comes back approximately, it says, to 4 decimal places, so 1.8083 it looks like, because it would be 2.8. The 8 would make the 2 round up to a 3. And then the next one is just what is the log of 1/2. And that one on the calculator comes back negative 0.30102, so 301. Don't really need to end with a 0, even though it says 4 decimal places. Having a 0 at the end, you can always drop those if it's after a decimal point. Alright, this next one, number 12, wants us to change the base, so I have to use the change of base formula, which, remember, key part with this is whatever the base is, which is a 4 for this one, base will go to the bottom. So for the change of base, it does specifically tell me to use common logarithms, so this is going to be log of 24, whatever's on top is what's inside, and then over log of, and again base goes to the bottom, so 4 must be in the denominator. So really at this point it would just be a typing into the calculator exercise. So I'd do the log of 24, then divide it by the log of 4, and I would get an answer approximately 2.29. It says what, 4 decimal places, so 2.29248, so 25. The 8 would make the 4 round up. For 13, this just wants me to do some conversions, so notice it's in log form. I don't see a base, so I can write a base of 10 for myself, just to remind myself that the base is 10. And how we can start this process is whatever is inside will be by itself, so x will equal whatever the base is, which was 10, raised to the only thing I haven't used yet, which is the number on the other side, so 12. Part B wants us basically just going the complete opposite direction, so this one would be, again, start with what's inside, so x will equal, and then it will be log of whatever the base of the exponential is, which the base should be the 4, and then it will be of what, again, I have not used, so in this case 1.2. For number 14 here, it just wants us to express this as a single logarithm. I do have a rational coefficient, so that, remember, is really the first thing that we deal with, which is the, let's move those numbers up as powers. And I'll let you kind of make a decision on whether you want to leave that as a 2/3 power or really write it as a cube root of z squared. I'll go ahead, just for practice sake, rewrite it in that radical form just so you can see it. But this would turn into log base c of x to the 5th, then minus log base c of y to the 4th, then plus log base c of z to the 2/3. Now all of the terms that come back positive should go into the numerator, so all of this will get to turn into a single logarithm as it says in the problem itself. So I know it's going to start with log base c because that's what all of the logarithms were. And the two positive ones, or the two that have either a positive sign or a plus sign in front of them, will go into the numerator. So in this case that would be the x to the 5th, and then it would be times the z to the 2/3, which again I'm going to rewrite that in radical form, where the denominator becomes the index of the root, so it's a cube root of, and then what power is in the numerator stays on the z, so that would be z squared inside. Then it would be all over whatever is negative. So in this case there was only one term that was negative or had a minus in front of it, so there's only going to be one thing in the denominator, which is the y to the 4th. If we move on to 15, this is one that actually starts with a radical, so right off the bat I would want to rewrite this using an exponent, so this would be log of y cubed z, and then it would really be like to a 1/5 power because it's all inside of a 5th root. So again, remember the index of the root is going to the denominator of whatever is there. Now I have kind of two options. I could move that out front if I wanted to, or I could just apply it to the two powers that are inside. I'm going to go ahead and just do the apply to the two powers that are inside and worry about the separation here in just a moment. So this would turn into y to the 3/5 and then z to the 1/5. Now because it's multiplication on the inside, I can separate this into two logarithms. So this would be log of y to the 3/5, and when I separate multiplication it's going to turn into addition in between the logarithms. And then my very last step will be to deal with those exponents and move them out front. So keep in mind the power that's there can now move in front as a coefficient. For my final result, which I'll put up on the actual answer line, which is 3/5 log of y. And if you want to put parentheses around the y, you can. I'm just going to leave it separate. And then plus this one has 1/5 in front. And then log of z. And there we go. All right, now 16 and 17 here are going to have us utilizing some given info to try and solve for some specific other logarithms, if we end up having the ability to do so, which it looks like these two numbers I should be able to from the numbers they provided. So this first one, I need to try and find a way to rewrite the 6 that's inside using either a 2, a 5, or a 12. So if I think of, okay, what are some ways using either a 2, a 5, or a 12 that I could maybe rewrite 6? Well, the first thing I can think of out of those options would be to do log base A of, and then do 12 divided by 2. I feel like 12 divided by 2, that should equal 6, so I'm just going to rewrite it that way, which should then be able to split into log base A of 12, and because it's division, I'll use subtraction this time, so minus log base A of 2. Now, they provided me with those values, so log base A of 12 I should be able to replace, so this really is going to be 1.195, then minus whatever the log base A of 2 was, which was apparently 0.333. So if I go ahead and type into the calculator 1.195 minus a 0.333, that comes back as my final result of 0.862. Now looking at 17 to make 20, I feel like 12 is probably not going to be very helpful, but maybe some combination of 2 and 5. Well, 2 times 5 would give me 10. If I multiplied by another 2, that would give me 20. So I really could maybe say that that's really the same as 2 times 2 times 5, or 2 squared times 5. So I'm going to rewrite this 20 that I had on the inside as really 2 squared, which is 4, times a 5, which is in fact 20. So that still is an equivalent statement. Because that was a product inside, I should be able to separate this into log base A of 2 squared plus log base A of 5. Now that power that I ended up having on the 2, I could actually move out front and make a coefficient, so this also can be rewritten as 2 times log base A of 2 added with a log base A of 5, which both of those values were provided for me, so this is really just going to be 2 times the 0.0333, and then added with the log base A of 5, which was a 0.774. So if I go ahead and do 2 times 0.333 on my calculator plus 0.774, that comes back as a 1.44. And there we have it. Now the next one, number 18, is relatively simple. It's just taking advantage of recognizing if I compose an inverse inside of it, or sorry, a function inside of its inverse, then they should cancel each other out. The base of natural log, remember, is a base of e. So since that has a log base e and I'm taking an exponential with base e inside, it's going to cancel each other out and just really leave whatever the exponent is. So this one was as simple as just recognizing those two functions do cancel each other out, so it should just leave whatever the exponent is. Different approach we could have done would have been to move that x plus 3 out front. So a different way would have been, or sorry, not x plus 3, but x plus 6 as a coefficient. Then that would have left the natural log of e, which the natural log of e has a value of 1. And since I have 1 multiplying with x plus 6, that would just remain x plus 6. So a different way of thinking of it that still gets you the same result. But I think the first way, recognizing that they're inverses, is a little bit more efficient. All right, on numbers 19 through 22, it just wants us to solve. So I'm going to scroll back down. So the instructions are just barely off the screen. That's why I scrolled back up for just a second. But I just would need to solve for whatever x is. So this first one, notice I have logarithms on both sides. So my goal initially is to find a way to combine them. So the 2 logs on the left, actually let's just double check. All 3 of them do have the same base of 3, so that's good. But the 2 logs on the left being separated by this minus sign should let us know, okay, because there's subtraction between those two, I can combine them and utilize the division idea. So at this point, notice we have the same log on both sides. So since both sides have log 3, the only way that they can be equal is if the inside of the one on the left equals the inside of the one on the right. So I'm just going to go ahead and set that up off to the side here. X over 4 should then equal 2. Well, that's manageable. All I'd have to do is multiply by 4 to arrive at my solution of x equals 8, because the two 4's on the left would cancel out, leaving me x. And so x equals 8 is also a reasonable answer, because the only x I would need to replace is right there. It already is a positive number, so it at least passes that quick little double check of, can I actually plug that back in? Moving on to number 20, it's got a very similar start, but notice the right side this time is not a logarithm, so I won't be able to do the cross out the logs or drop the logs situation. Here I, though, will need to actually recognize that it's now a plus in between, so instead of me dividing like I did in number 19, I'm actually going to multiply it. So this would turn into log base 2 of, and I'm going to go ahead and just multiply the x through the other two terms, so x times x would turn into x squared, and x times a 4 would give me a positive 4x. So hopefully that's not too big of a deal that I'm kind of combining the idea and truly multiplying them together without me writing it as a product first. So I just distributed the x through the other parenthesis basically. So now I'm kind of at a place where I'm stuck. I have a logarithm equaling something that's a number, so I can't just cross out the log, but what I can do is convert from this logarithmic form into exponential form. So keep in mind what I would do is I would take whatever's inside and start with that, so x squared plus 4x, and that should equal whatever the base is, which is 2, being raised to whatever the power is, which is the number on the other side. So if I go ahead and maybe simplify that number, x squared plus 4x is still remaining unchanged, but the 2 to the 5th on the right really is 32. So since I have a power of 2 involved, this seems like it's fitting more of a quadratic style. So I'd probably want to get 0 on one side like I normally do with quadratics. And this would turn into x squared plus 4x still, but now minus 32. And now set equal to 0. So it kind of tells me right now, based upon a lot of things I've done, that I probably want to factor. So I'd want to multiply to that negative 32 and add to a 4. So to me that seems like that would be a positive 8 and a negative 4. And if I go ahead and set each of those equal to 0, setting x plus 8 equal to 0 gives me negative 8, and setting x minus 4 equal to 0 would give me positive 4. So let's do a quick double check. Can I plug both those numbers back in? Well, if I did negative 8, well, the second one I can already tell it needs to be a positive number regardless, so that negative 8 is out. Let's try number, or the number 4 in this case. So 4 plus 4, that stays positive with this first one, and plugging in a positive 4 in the second one checks out. So it seems to me that my only solution for this one, even though I got 2 initially, is going to be the x equaling 4. Alright, moving on to 21. This one, if I look at what I have, I've got exponential equation. I've got a base of 3 and a base of 9. I feel like there's a way I can make them match. That's always the first thing I try. I could rewrite 9 as 3 squared, so that's, I can have this as 3 to the 5 plus 4x, then being equal to 3 squared to the x, which a power to a power I would multiply, so that's really just 3 to the 2x. Well, once those bases match, which I've made happen, it really should just, the only way that they can equal, it should just turn into something where it's the two powers then must equal each other. So I'd have 5 plus 4x must have to equal 2x. So in going through and solving that the rest of the way, I would subtract 4x from both sides just to get the x's together. That leaves me with a 5 equaling a negative 2x. And so it seems reasonable to me to get x by itself. I would just divide by a negative 2 to arrive at my final result of x will just equal a negative 5 over 2, or negative 5 halves. If you wanted to write that technically as a negative 2.5, I'd be okay with it, but why do extra work and type it into the calculator if we already had a fraction that was in reduced format anyway? Alright, moving on to number 22. This one wants us to just solve, but this time I don't have the ability to make the base e match the base 6 on the other side, so I'm kind of stuck trying to use the same strategy as what I did with 21. So what I can do is maybe introduce the concept of a logarithm, so maybe take a natural log of both sides. The reason I would choose maybe a natural log over a common log is because the natural log actually is an inverse of the base that I had, which was e. So that should mean that the natural log and the e cancel each other out, leaving me just 2x equaling the natural log of 6. So what I could at this point do is just say, well, I'll just need to divide by 2 in the next step. That should cancel the 2 in front. And now my x is all by itself, and typing into the calculator, I'd get the natural log of 6 divided by 2 turns into approximately 0.896, it looks like. If I were to just maybe go 3 decimal places, if you wanted to go 1 extra, you could say 8959, but as long as you're at least 3, I'm going to call it good on that one. Moving on to what looks like our last few. So number 23, it says that the population of some country doubled in 30 years. So what was the exponential growth rate? Well, this is one of the more recent formulas that we had. Remember, for this one, if I needed to come up with what the growth rate is, that's really the k. So k was equal to, when it's doubling, it'd be the natural log of 2 being divided by the time it took to double. So for this one, the k is going to equal the natural log of 2 being divided by 30, because that was the time provided. And if I go ahead and type in natural log of 2 and divide that by 30, it gives me a k value that's approximately 0.02310. So it did say round to 4 decimal places, so the 0 after the 1 would just keep that as a 1. So there's my k value. So k equals for this one 0.0231. Moving on to number 24, this one gives us an amount that was invested. So this is going to use the P of t is equal to our initial investment times e because of the word continuously, and then to a power of k times t. So it does give me an amount that it turns into in a specific time, so I should be able to solve for the interest rate, which is what part A wants anyway. So I'll just substitute those things in. So $4,934.71 should equal the initial investment, $4,000, times e to the k, which I don't know, but then times t. Well, this specific amount was related to 6 years. So if I go through and just do my steps here, it's going to be divide by 4,000 first. Which 4,934.71 divided by 4,000 turns into, for me, a 1.2. I'm just going to list out as many decimals as possible to stay as accurate as possible. But that would equal my e to the k times 6. So to cancel the e, just like we did not too long ago, I'd introduce a natural log. And so those should cancel, and really I just need to divide that result by 6 then. So keep in mind I would do the natural log of this long number first, close the parenthesis, and then just say divide by 6, and that should give me what the k value is. So our k value is going to equal, it looks like, the natural log of that number divided by 6. And I get 0.03499999, so I'll just call that 035. So now that I have my interest rate, I should be able to come up with my growth function just by plugging in the parts that I know. So this would be the P of t is equal to the initial investment, so that's still 4,000. That's always going to be 4,000 for this problem, times e to the k I just found, 0.035, and t because I'm writing a function of t. So now it says, what is the balance after 10 years? So for part C, that's really just figure out what is P of 10. So if I type in 4,000 times e to the 0.035, but then times 10, that comes out as an approximate value of 5,676, and rounding to pennies would be 27 cents. As far as finding the doubling time is just going to be, once again in this case, now it's the t is equal to the natural log of 2, but then divided by the k, which we already solved for as the 0.035. So if I did the natural log of 2 and divided by the 0.035 on the calculator, it comes up with my time value, in this case being 19.8 years. Because remember, with these problems, the time is always in terms of years. And then moving on to our very last one, I just need to identify which of these graphs is potentially the one that's being represented by the function f. So if we look at what we've got and try and identify the parts that maybe are potentially changing, well, I've got some form of shift to the left 2 places, or sorry, not to the left, but I have some subtraction by 2. That would actually move it to the right 2 places, and then I have subtraction outside by 3. So this is right 2, and this is down 3. So I'd basically look to see, okay, if I think in terms of the original parent function, which in this case is x and 2 to a power of x, the numbers I would think to maybe plot if I were to actually have to graph it would be like those points, -1 and as a power on 2. That would really be like 1 over 2, which is 0.5. 0, which should just give me 1, and then 1 would give me 2, and 2 squared would give me 4. And then a horizontal asymptote, because this is exponential, of y equals 0. If I think of what points should happen after I do the 2 steps that it said, well, going to the right 2 should add 2 to x, and then down 3 should take away 3 from y. So if I maybe just figure out what those points are, increase the x's by 2, so that would be a +1, a +2, a +3, and a +4. And then decrease all of the y's by 3, so 0.5 take away 3 is -2.5. 1 take away 3 is -2. 2 take away 3 is -1. And then 4 take away 3, that would actually be +1. So if I maybe just on this first grid tried plotting those points, 1, -2.5 would lie on that graph, so far so good. Seems like that actually, out of all of the other ones, -2.5 would be there on that one, -2.5 would be here, -2.5 would be there. So it seems like we've already got it, but just to kind of prove the point, I'm going to go ahead and plot the other ones. 2, -2, that one was still on it. 3, -1, that one was still on it. And 4, +1, look at that. And if we wanted to, our horizontal asymptote, we could have also kept track of. If I just moved down 3 places, 0 would turn into a -3. So I could have also looked for which graph has a horizontal asymptote at -3, which it looks like at least 2 of them had. Looks like part C was down at -2, so that wasn't quite far enough. And then the last one doesn't even really look like an exponential. That one actually looks more logarithmic anyway. So as far as my final answer for this one, we've hopefully committed to A by this point, but when it comes to taking the test, I'd recommend maybe just using the grid on part A, plot the points that you know should be on the graph, sketch it, and then you could maybe just compare with the other graphs if it didn't line up perfectly like this one did for me. I got kind of lucky that the first grid actually was the graph that I wanted, but again, it could have technically been, if this was scrambled, a different result, but I still could have maybe drawn the line and then just compared, okay, which one looks best fitting to whatever I just plotted. Anywho, hopefully this has been helpful, having the solutions for each of the problems on the review. But if you have extra questions, just reach out, let us know, and we'll try and get them clarified for you before you start your test. As always, I appreciate you guys taking the time watching the video, and we'll catch you next time.